All right, so this video is going to be on nucleophilic aromatic substitution. And so if you saw the previous video, which you should have, I mentioned not knowing how to make a phenol. And we'll actually learn how to make a phenol in this video. So that's cool. Now our synthesis of benzene derivatives is going to be off the chain. We've got an alkyl halide, or aryl halide, sorry, in a nucleophile, and then we substitute that halide with a nucleophile. Okay, that's nucleophilic aromatic substitution as opposed to the electrophilic aromatic substitution. Now it works out. I'm gonna call it NAS just because I want to sound cool. So NAS occurs via two mechanisms, and both of these are gonna look really familiar, and they're gonna more or less contradict the rules of substitution and elimination, but who cares? Because that's how chemistry is, right? So we're talking addition, elimination, and then elimination, addition. So this is the order of the steps, right? So let's talk about the addition, elimination first. And then after that, we'll go and touch up on the elimination, addition process, okay? Now, the reason why I say these are going to contradict what we've learned for substitution elimination, that is because we were working with just sp3 hybridized carbons, right? But obviously aryl groups are sp2 hybridized, and so that's why. But we just kind of have to use this as an exception, right? So it's also going to be some specific conditions. The addition elimination occurs only with aryl halides with electron withdrawing groups at the ortho-para position, okay? Electron withdrawing groups. And then elimination, addition, it doesn't require electron withdrawing groups, but it requires some very extreme conditions, okay? Like very, very basic, strong base, very hot, very pressurized sometimes. The crows have eyes. Oh, wait, that's the hills. Whatever. Anyway, addition, elimination. All right, so this process, again, we have an aryl halide with the chlorine there. We got a nitro group because we need that electron withdrawing group. And then we have a hydroxide, which is our super cool base, right? Our nucleophile. And we get substitution there, right? Nucleophilic aromatic substitution, done. But the mechanism, all right? So, well, first, actually, let me mention that the nucleophile needs to be strong. It could be your alkoxide, it could be your amide, NH2 minus, it could be your sulfide, SR minus, right? Or it could even be your NH3 or your NH2R, right? And those are going to be under drastic conditions. So these, in general, just need to be the right kind of conditions in order for this reaction to occur. And so drawing out the mechanism, you'll understand why that electron withdrawing group is required, right? So let's say we have the nucleophile attack that position with the chlorine on there, our leaving group, right? And we have this tetrahedral intermediate with the negative charge on the benzene ring, of course. Now, what we can do is draw a resonance structure, and that actually helps us explain why we need it at the ortho or the para position. So as you can see, the negative charge is on the ortho position right now. I had to redraw those arrows for you. Let's place that negative charge directly next to that nitrogen, because remember that nitrogen in the nitro group is positively charged. Sorry, I missed it on the first one or the second one. But having those positive and negative charge next to each other helps stabilize that charge, right? That's why we need the electron withdrawing group. If we had just a regular electron withdrawing group that couldn't form that resonance structure like this nitro group does, it would still help stabilize it just because it's typically an electron withdrawing group, right? And it's going to help stabilize that negative charge inductively or however, right? And so this is exactly why we need that electron withdrawing group. And then at the para position specifically, because if it were at the meta position, the resonance structure, we wouldn't be able to form a resonance structure where the negative charge was directly next to that positive charge. okay? And as you can see, our resonance structures here put the negative charge at the ortho position as well as at the para position. Now we can shuffle it back around to the other ortho position, right? You can see that these guys are the same. And then now what we can do is just put that negative charge back down, creating a pi bond and forcing that chlorine to leave. And then that gives us our desired substituted product with the OH there, okay? Notice that the OH substituted the chlorine directly. And this is going to be in contrast to the next mechanism. But ortho or para electron withdrawing groups are essential here, okay? Now, there's a couple other things we want to add to this particular mechanism, or at least the some conditions, criteria, etc. So the more electron withdrawing groups that we have, the faster this reaction is going to be. And this makes sense, of course, because of it's stabilizing the negative charge, i.e. the intermediate. And so if we have more electron withdrawing groups on there, we're actually stabilizing that charge even better, right? It's going to help neutralize that negative charge, making it more stable. And so that's going to lower the energy of the transition state and make the reaction move faster. The same idea goes with the electronegativity of that leaving group. So the faster the reaction, the reaction is going to occur faster if we have a more electronegative atom there, like fluorine, for example. And that's just because you get a more polarized carbon-fluorine bond, and that's more susceptible to nucleophilic attack. So here we go, comparing. This is kind of more or less going to be like a depiction of those two rules here. So we have a scenario where we have a nitro group at the para position with the chlorine, and then we have it at the ortho and the para position. So comparing the first two is just showing you the first criteria, right? The more electron withdrawing groups, the faster that reaction occurs. So the middle one reacts faster than the one on the left. Now, the substitution on the right is basically a chlorine is swapped out for a fluorine. So that's showing you that the more electronegative atom is going to react faster. And so the trend is increasing as we go from left to right. Okay? All right, so that was basically those two criteria in a nutshell. Now let's talk about nucleophilic aromatic substitution by the elimination addition mechanism. Okay? All right, so remember, this one required extreme conditions, right? So we have this aryl halide, and we have sodium hydroxide, and we have hella heat, hella pressure. Then the second step would just be acid to help neutralize the reaction and kind of move on, right? So that's going to get your phenol product. So like I said, you're going to learn how to make that. We could technically just have benzene, do the halogenation step to get us our chlorobenzene, and then do this crazy step to get our phenol. And then now we can move on and do our Friedel-Crafts to get that methyl group in the para position. Yeah, you're probably not going to get what I'm saying if you didn't watch the video previous to this. But the mechanism is elimination first, right? So we're approaching it like every elimination. You remove that beta hydrogen and then it kicks out the leaving group. So the intermediate in this case is fancy because, oh my gosh, why are all these rings garbage? My apologies. My iPad doesn't want to correct it for me and make a beautiful hexagon, so I'll just draw it myself. It's gorgeous without the computer. I don't need a robot to make 6 membered rings. We got this benzyne intermediate. So remember alkyne, YNE, benzyne, right? It's got a triple bond in it, and that OH, the hydroxide, attacks the triple bond, and that kicks the pi electron over and gives you a negative charge on the benzene ring, right? We pretty much have the likings of our phenol. It looks just like it, but we do need to, sorry, I didn't put the water in that first step, the product of the first step, and then it protonates the benzene ring, and then now we get our phenol product, our desired product, as well as hydroxide back, and then now we can make another one, right? And so The thing here is we made that benzyne intermediate. It's super reactive and it's going, we have two spots, right? So notice I put the hydroxide on the spot where the hydrogen was, right? But if you, the circled carbon where the chlorine was can also be substituted if we attack there as well. So let me show you in red where that, what the product would be if that red arrow did the attacking. And we put that negative charge on the top now, and then the hydroxide, the OH on the right side now. And then we protonate, we get our product, and I'm going to put them side by side so that way we can compare and contrast. Obviously, these are the exact same thing, but just the point is that if we had a substituted benzene, we would see that they would be very different. So let me throw a methyl on here for you. Now you can see that the OH is meta to the methyl now, or it's para to the methyl now, okay? And so that's one of the key differences in kind of identifying the mechanism for this particular substitution. The benzyne intermediate, although it's high in energy, does actually suggest, or I guess the products do support that mechanism. So if we form that benzyne, then we can say, okay, well then now that makes sense. We get the meta and the para products. So that's actually how they come to plausible mechanisms. It's just what makes sense. We see our products, and now how can we actually make these products, and and then there you go. So this sodium amide right here, remember you can have NaNH2, which NH2 is a minus, and then we can also have like a K there, right, potassium. So we just have to know that this is a salt, not to be confused with just NH3, but in this case it does yield the same thing, or the same, it's the same mechanism more or less. So we form that benzyne intermediate with the methoxy on there. Notice that's an electron donating group, and we're still moving forward with this. That's because the conditions are going to be extreme. And we form that benzyne intermediate, which of course can get attacked on either side. So you'd get your para substituted product or your meta substituted product, so, which is pretty cool, right? Because normally that methoxy would be an ortho para director, but we just put a group on there in the meta position. So that's important to note, because now we've got more tools in our toolbox to form desired products. There is, of course, that other hydrogen, right? I'm moving these pi bonds because it's not going to make sense otherwise. But remember, the pi bonds just move around because of resonance, right? We formed this benzyne as well. We had that like proton that was ortho to both of those substituents. We can, of course, remove that, which would yield one of the two products from the original mechanism, but then we would also form a new product where the methoxy is ortho to the NH2 group, right? And so that's if we attack on either side of that benzyne. And so we actually get three different products because these original substituents were meta to one another, and we can form two different types of benzyne rings. Okay, so keep that in mind. There's lots of possibilities when we are doing these mechanisms, and so just follow your heart because these mechanisms are something we've kind of done before, right? And we just need to remember a couple extra things like extreme conditions and electron withdrawing groups. Okay, so let me draw. I'm drawing this ring much better now. I think this looks gorgeous. A little bit of green, a little bit of red, a little bit of blue. If you're gonna do it right. You could put that in a textbook, y'all. That wasn't a robot. That was Jess. Although I might be kind of robotic sometimes. That's me drawing the resonance, right? Like this is the pi electron overlap, and they're all just doing their thing, making benzene hella stable. But if we removed a proton, we would form that benzyne, right? So we have the red and blue pi overlap. That's one of our pi bonds. And then the sp2 hybridized orbitals make up a second pi bond. And that's where that benzyne ring comes in. As we know, there are sp2 hybridized. So the 120 degree angles, they're not really parallel with one another, and so the bond angle is highly unfavorable, and that's making this bond very weak and also highly reactive. Okay, and so that's why this intermediate is so reactive and unfavorable, and we require those extreme conditions. It's also been the cause of many laboratory accidents, and so it is a very it's a dangerous reaction, but on paper it's all good, right? All right, so let me know if you have any questions. Have fun. Bye.